too. Bless up.
Canvas.
Oh, thank you.
So probability density function of a continuous random variable, just to recap that for continuous random variable, probability that random variable x takes value exactly certain value. I call it, let's say, exactly certain value is going to be this. That is the major characteristic of this random variable and continuous random variable. In this random variable, we have some non-zero values for so this sort of expression of continuous random variable is zero, guaranteed. And I gave example why it is zero. So the definition of the PDF is basically stemming from the definition of cumulative distribution function. So we know that cumulative distribution function f sub x taking value x is by definition it gives you the probability of random variable x takes value less than or equals x for all values of x from that entire range. So you can start from negative infinity all the way to x, and x can go all the way to positive infinity. So once we have the CDF, we can find the PDF, which is basically derivative of PDF, I mean probability density function. So the notation log is f sub x is basically log is f sub x, argument is log is x. This is your random variable. This is your random variable, and random variable takes values that is represented by value of RB and random variable. This is value. So it is basically the derivative of the CDF with respect to x. And you know from Calc 1 the derivative. This is basically the step size. It discretize the continuous function with the step size. This is step size. It discretize the continuous function. You drop it in such a way that you make it very, very small with h tends to 0. Then you can actually define the derivative as such. F sub x plus h minus f sub x over h. And because in reality, practically, we cannot have h equals 0 to h cannot be 0. H is not 0. H tends to 0, but h cannot be 0. Practically, we will have some value of a value of h. This is step size. So this is x. Negative infinity to positive infinity. So this represents x. Then we have the h is basically this small step size h. H tends to 0. Limit h tends to 0, but not exactly 0. But we are going to utilize this h to come up with the probability of the random variable that can take value between this is your x and this is your x plus. So what is the probability that random variable x takes value in this interval? And this interval is nothing but the rectangular area. So rectangular area is whatever area you see times this h. And this is actually better illustrated in this figure. Okay? So I uploaded the new slide. So in the old version of slide you see this. So here you see x plus dx. So dx you can think of this as h, x plus dx. Probably it is basically whatever the area is. If instead of x plus dx, if you see, if you define two integrals a and b instead of x and x plus h, So you can have definitely four different limits. So this is the lower limit, this is the upper limit. In that case, this area is basically the probability of having a random variable in this interval. Now, one thing, it's quite trivial in the sense that you saw this sort of integration before. One thing that is very, very important is that this period that is coming from this period, which is f sub x, and you take the derivative of the cumulative distribution function with respect to x. Okay? So this period has to be greater than or equal to. So that is one condition. Please do not get confused that that's where most people make mistakes here. So when they see this sort of bell-shaped curve, so they think that this is one, but it is not the case. This is not one. You will have some non-zero value, or what you can say that this is positive, greater than that. Okay? But this is not one. Please do not get confused. The other thing is that when you take the probability of a random variable that has a distribution defined by the probability density function f sub x, okay? Then you take the integration of f sub x. This should be known. This distribution is known. So if you know this, then you can just integrate, and it is simply area under area under the bell-shaped curve with from limit a to b, where b is the upper limit, a is the lower limit. Now, again, this is also quite known. The mistake where people do, this is where it is there. If I ask you, what is the probability of continuous random variable x that takes value a less than or equals x less than b? Okay? So what would be its probability? It is exactly the same as this one. It is exactly. Here I put less than or equals, here I put strictly less than. So it does not matter less than or equals. For continuous random variable, it does not matter if it is less than or equals or simply less than, or less than or less than equal. It does not matter. Why? Because we know that a less than or equals x less than b is same as probability that a less than or equals x less than b is same as probability of a x equals a plus probability a less than a. And I know that for continuous random variable, this guy, because for continuous random variable, the random variable takes value exactly a is 0. So that's why for continuous random variable, less than or equals or equal less than, it does not matter. So you can just put less than or less than or equal. So this is the main point in this slide. The other thing is that when you define the period, when you know the period, then you can actually derive the CDF the other way around. CDF is basically negative infinity to x, you integrate negative infinity to x, and this should be known. This PDF, probability density function, should be known. S, I did not put x because x is the upper limit of this integration, so therefore I have s as the integration variable. And the other property that you should know, here you will see many problems, many example problems or end of chapter problems. You will see you will be utilizing this. Okay, for your homework problem, you will be utilizing it. Where you have negative infinity, positive infinity, f sub x, x. The total integration should be 1. So said initially, that people make mistake here that they think that this gap is one. No, no. It is the area. It is the area of the entire area. Entire area has to be. Okay? And that's one. Now, even though I mentioned this several times, but here for continuous random variable x, the probability that x less than 5 is exactly the same as probability that x less than equals 5. Why? Because I know the probability that x equals 5 plus probability that x less than 5. So this probability is basically probability equals x equals 5 and x less than 5. And this is basically so. Now let's implement this concept to this example. Yeah, this example is not from the textbook. So let's go to this example. In this example, we have a random variable x that takes a real number uniform. It's an uniform random variable, but it's a continuous variable. So solution. So x is a continuous, but it is uniform random variable taking value from interval n including n, where I know that b has to be strictly greater than a. So we want to find the series of random variables, which means by definition it is probably f sub x, which is the serial mathematical notation, mathematical function representing serial. So it's basically giving the probability of the event. Now look, I think that you see this is a real line. It could be negative infinity to positive infinity. Okay. And here this is your x random variable x can take any value from negative infinity to positive infinity. I am going to mark the interval. Yeah,
It's the first time you see my foot, right?
so therefore this interval
I was in crutches.
this interval is your now length. If you recall guys, chapter 2, we talked about probability, where let's say we have A equals 2, 3, and then we have sample space S equals, let's say, 1, 2, 3. Okay. So we find the probability of event A is basically length or cardinality of set A over cardinality of set S. In other words, this is the length, which is basically number of elements, and this is also length, basically number of elements, which is basically 2 over 6. You guys practice already. 2 over 4. There are 4 elements. So here it is basically the number of elements. We could actually write 4 because we could count the number of elements. Here in continuous random variable, we cannot simply count how many points. So here I want to find the probability of random variable x takes value between 1 A to A and B. So let's length of this part is b minus a. So this is length, and this is length. Okay. Now I am going to write condition if, let's say, x less than a. Yes. Here the random experiment here is that x has to be chosen between a and b. The number has to be chosen between a and b. Outside this range, it's an impossibility. Okay. Now, I need to find what is CDF. So CDF, when I find CDF, okay, to find CDF, we need to find f sub x, taking value x, which is by definition probability that x less than or equals x for all values of x from the entire group. So therefore, if I have the condition x less than any value of x less than a, in that case, what is the CDF? F sub x, taking value x, which is by definition probability that x less than or equals x. What is the probability? X less than a. It is outside this interval, and it is an impossible event. Because it is an impossible event, therefore this probability is probability non-event. So f sub x is how about if a less than x less than or equals b. So here I put if a less than, less than or equals, here I put less than. So in that case, x is any value in between. Therefore, you should have a probability. So in that case, f sub x, which is by definition probability that x less than or equals x, is going to be length of interval ax over length of interval a, which is basically x minus a over b minus. Now we have the last condition, which is if x greater than or equal to b. So that will cover the entire real line. So in that case, f sub x, which is the CDF, which is by definition probability that x less than or equals to x is going to be. So now that x can take all the way to b here, and after x greater than b, it is an impossible event. That probability is 0. So therefore, so you can just think of it is length of AB over length of this one. So which is basically b minus a over b minus a, which is 1. Okay. So like that, we covered the entire real line. So therefore, we can graphically write we can graphically cannot rewrite as such. So, let's say this is my this is my A, this is my B. So in that case, this is your f sub x, y axis is f sub x, and x axis is x.
Should
That
be
can be
when you get from
very
background.
Now, look at the condition. So x less than a is basically 0. So you go all the way from negative all the way here, but not including a, not including. And then you go all the way from A to B, not including B. And then, so this is basically f sub x is basically 1 minus a times x minus a. So you'll have a linear side. Okay, so you just it's going to be linear. And then after that, when x greater than or equals b, that time, yeah. So therefore, you have this point is your 1. This point is your 1. And here you have 0. So this one is basically x minus a over b minus. So you can graphically show the CDF as such. Mathematically you show the CDF. Mathematically. Mathematically, the CDF f of x is basically, it is 0 if x strictly less than a, it is x minus a over b minus a if a less than or equals x less than b, and it is 1 if a x greater than or equals b. So what you should notice here is that we have this open circle, which means at this point, f sub x is not differentiable. You cannot differentiate at this point. So that's how you should come up with the CDF. So if you have the CDF, then finding PDF is a piece of cake. Finding PDF is a piece of cake in the sense that you know the function already, and PDF is simply probability density function is basically the derivative of the CDF with respect to x. So which is basically this equation. So all what we need to do is we just take the derivative. So derivative of this quantity is going to be 0, constant, okay? And then we have this continuity here, and then derivative of this quantity with respect to S is simply 1 over B minus A, and then after that we have C. So we can write the here probability density function. Probability density function PDF, which is denoted with f sub x, is simply derivative of the CDF with respect to x, which is basically 1 over B minus A if A less than or equals x less than B and it is 0 otherwise. So mathematically you simply write, because we have to write the answer. So f sub x is mathematically you write 1 over B minus A if x A less than or equals x less than B and it is 0 otherwise. Okay. And graphically, you can draw. This is your x-axis. This is your PDF. And this is the color. So this is your f sub x, and this x-axis is x, then from negative infinity to positive infinity, and it is simply open circle here, open circle here. So this is your A, this is your B, and this I is going to be 1 over B minus. 1 over B minus. That's how we define the probability density function. So again, this is fundamental. The most important actually here I have a simple piece of code, and you know that from this picture very well. You can, it's basically the same code that I copied from earlier, where you can use uniform PDF, uniform.pdf, uniform.cdf. So only addition you have is this PDF. Probability density function. There is a method already. All what you need to do is to get the x values. And then so this is optional, and you can just pass this scale G minus alone. Okay. So that's how you determine the PDF value, CDF value, and then you simply plot x value, PDF value, and x value, CDF value. Cumulative distribution function and probability density function. So as you could figure out that if you know the theory properly, then implementing this function from statistics package is a piece of cake. So in this example, we have A, B equals 2, 6, which means that we have A equals 2, B equals 6, and then you can just pass plot uniform distribution. This is the function name. This is function name, and you pass of these two parameters, that will come right here. So A will be replaced with 2 and B will be replaced with 6, and then these pieces of code will be executed. So where you first define the linear space between A minus 1 all the way to B plus 1, 1000 point, and then determine the PDF values. Probability density function values in the variable PDF value, cumulative distribution function values in the variable CDF value, and then all what you are doing here, you are just simply plotting. You can practice that. Now, it's very similar, this example is very similar to the previous example, except that you have, the random variable x, it follows an exponential distribution. So transmission time x of the messages in a communication system has exponential distribution, which means probability of the event. This x represents the transmission time. X greater than x is e to the negative lambda x, where x is strictly greater than 0. Now, if you want to determine, here is the trick, guys. If you want to determine CDF, what you will need to do, solution, if you want to determine CDF, what you will need to do is to determine probability, CDF of random variable is taking value x. I'm not writing details here. By definition, it is probability that x less than or equals x. So this is by definition. But this by definition, this is your CDF, but you are given probability that x strictly greater than x or x greater than x. Here for all values of x in the real line, but here you are given x greater than 0. So to get the CDF, all what you need to do is given the fact, given that probability of x greater than x plus probability, I'm going to take all the less than or equals and greater than everything. So x less than or equals x. So this summation is going to be 1. This is what we know already, because I'm taking the entire real line. So here you can see that we can keep this part to the left side. So x less than or equals x is basically 1 minus probability. This is the only thing. Okay? So now this is given to you. So by definition, it is your CDF, and it is 1 minus. This part is basically e to the negative lambda x. E to the negative lambda x. Okay. So this is the answer. X greater than 0 for x greater than 0. We have 1 minus e to the negative lambda x. Now look, when you define f sub x, it has to be from the entire real line. It has to be defined over the entire real line. How do you do that? So if x is strictly less than 0, so again I'm going back to the condition. If x is strictly less than 0, then you see that this is an impossible equal. So if x is strictly less than 0, then f sub x is going to be probability that x less than or equal 0, which is basically it is an impossible event. It is an impossible event, and then if greater than 0, x greater than 0, doesn't matter if it's greater than or equal or strictly greater than 0, it is simply f sub x, x. You can just put x greater than or equal. It is 1 minus 1 e to the negative lambda. Now, when you put x equals 0 here, if you substitute x equals 0, it will be 1 minus e to the 0 is going to be 1, 1 minus 1 is 0. So it is 0 answer. So that's why it is less than or equal or strictly less than, it does not matter. So continuous answer. So mathematically, you write f sub x, x is 0 if x is strictly less than 0 and it is 1 minus e to the negative lambda x. So that is the final answer. That is the final answer. Now one more quantity that we need to determine is the PDF of random variables. The PDF of random variables probability density function of random variable x, which is denoted with f sub x, is going to be, by definition, it is derivative of the series with respect to x, which you can directly write. So you know that it is 0 for x greater than x less than 0. So it is going to be 0 if x is strictly less than 0. And it is, if you take the derivative with respect to x, what you see? This is 0 minus e to the lambda x is going to be to the negative lambda x. And then if you take the derivative of this quantity, negative lambda. That negative and this negative becomes positive, so you are left with lambda e to the negative lambda x. But you remember that for your next examples or exam, this is another thing to remember. For exponential distribution, the probability density function will be directly writing this expression. So if x greater than 0, so we will be greater than 0. We will be directly writing this expression. And what the meaning of this expression is, this is basically the source. Source value. So mathematicians say source value. What is source value? When x equals 0, so this is the maximum value. When x equals 0, this value becomes 1 and this becomes lambda. So here, this quantity is going to be lambda, and if it is f sub x, and you will see it is going to be. So this is your lambda. So that's what the exponential distribution is. Now, you can figure out what is going to be, it is going to be just opposite. This function is going to be just opposite. I'm not drawing graphically the series, it is just going to be opposite. See, when x equals 0, so it is going to be 0. Whereas it is x to 1 minus this quantity, so it will keep increasing. This quantity will keep increasing, so it is going to be like that. So it's going to, if it is x, it is going to, when x equals 0, it's going to be 0, and after that, it's going to be like that. So that is going to be your. That's all right. Graphically, this is what it will look like. Now I have this Python code here, corresponding to here you see that import x1. Again, it is from the statistics package, so it is x1 with the exponential distribution. Exponential distribution. Exponential distribution, you know that it is basically x sub x, it is lambda, it will be lambda. Well, lambda is the rate parameter, and it is also the value at source, which we put in x equals 0, the distribution value, the PDF value is going to be simply lambda. So, all what you will need to know is how you come up with the PDF value. So you can get the PDF value directly from the distribution formula, or you can use dot PDF, and the parameter is basically only one parameter, which is lambda. Lambda is the only parameter. Okay, so you can use dot PDF and dot CDF, but instead of dot PDF, dot CDF, here we use the exact expression of PDF, manual computation of PDF, and the CDF value, which is 1 minus exponential. All right, so I think you guys are waiting for the exam, so let's get prepared for the exam. Now, I would like you guys just keep the formula sheet, calculator, pencil, and now I would like you to have some space. You should be able to sit on the edge of the table. So one of you should sit here, the other one should sit right here. Okay? So make sure guys that you guys have some space in the